started now. Good afternoon, NOAA Library and everyone attending online. I have the pleasure of introducing our speaker this afternoon, Meredith Kurtz. She is a 2018 Knauss Fellow in the Ocean Acidification Program, and she works with an awesome team working on national and international ocean acidification science and policy priorities. Meredith earned her BS in Ecology and Evolutionary Biology from Tulane in 2013, and then afterwards she spent 2 years as a high school biology teacher in New Orleans. She then returned back to school at the University of Delaware, where she received her master's in marine policy in 2017, and she completed interdisciplinary research on the value of blue carbon in the Mid-Atlantic salt marshes. So without further ado, take it away, Meredith.
Thank you for the kind introduction. So the work that I'm going to be talking to you today is a part of a larger Sea Grant project that runs across 4 states in the Mid-Atlantic, New Jersey, Maryland, Virginia, and Delaware. But I'm not going to include New Jersey today, so sorry, New Jersey. We're just looking at the Delmarva Peninsula, and we're looking at barrier island systems, which are very dynamic ecosystems that provide a lot of different ecosystem services and other values to the societies which depend on them. So the Sea Grant project is trying to place value on all of those different variables, like biodiversity, the value of the beachfront homes, which tends to be the biggest number, as we all know. But the one that I focused in on was blue carbon. And for those of you that, was probably none of you, but for those of you that aren't familiar with the term blue carbon, that's sort of hot phrase right now to talk about carbon sequestration and storage in coastal ecosystems. And when I say sequestration and storage, I define those terms as sequestration being the active removal of carbon from the atmosphere, and storage being the inert carbon in the soil and the biomass. So I like to start out with this figure from a really good paper by Hapke et al. And it shows the long and short-term rates of change in the barrier island systems of the northeastern United States. And these are the systems that I'm talking about today. And you can see that both in the long term and the short term, they're retreating among the most fastest of all of the most quickly retreating barrier islands in the north region. So especially Virginia, they're retreating at about 3 meters per year. And there's a lot of different dynamics that go into play with why a barrier system might be retreating, or what's the word, starts with a P, or building out towards the ocean. And some of it is human caused, like in New Jersey, a lot of the stabilization may have to do with nourishing and human structures that are built to keep the barrier islands in place. For obvious reasons, people in New Jersey would love it if their second and third home would not fall into the sea, so they spend a lot of money on nourishment of the beaches. Whereas in Virginia, there's a different management regime going on. It's mostly owned by the Nature Conservancy, and they do not nourish the barrier islands. They allow natural dynamics to take place. And right now, natural dynamics looks a lot like barrier island retreat. And a lot of the reason for that is because of, well, it's kind of hard to say island to island what the exact cause is, because the geology of any given barrier island is different from the one next to it, and it depends on where the sediments are coming from and why. But when we talk about barrier systems retreating, we're often talking about runaway transgression. And runaway transgression is a term that refers to there's not enough sediment in the back barrier marshes, keeping the barrier system stable. That sediment feeds the barrier island, and more sediment can come down from other nearby systems. But when those wetlands thin up due to sea level rise, increased wave action, human activity, what have you, there's not enough stabilization action happening in the back barrier system. So the islands are more likely to run inwards. And I am not a geologist by training, so if any of you know that I am wrong right now, please do tell me afterwards so I can say it better next time. So we're talking about these barrier island systems as systems because they are very dynamic and interacting with one another, and they have to be considered as a whole sort of coupled system between the island itself and its back barrier marshes, because a change in one is going to affect the other one. And as we know, barrier island systems provide a lot of services to humans. Some of you probably work on storm surge protection, the biodiversity that's housed in the nursery environments. I'm sure a lot of you are intimately familiar with the value of coastal ecosystems. So this is a time lapse that I got from Google Earth Time Lapse, which if you haven't wasted hours of your life looking at it, I highly recommend doing that. It's extremely fun. And these are three or four of the islands that I studied, and it's only going to go from 1984 to 2016 before she has to start it again. Sorry about that. But I want you to focus in on Paramore Island and Cedar Island. And these two islands next to each other really illustrate how barrier dynamics can be very different, even when the two barriers are right next to each other. Paramore Island is much more stable than Cedar Island. Paramore Island has a rockier base, and it has like actual trees on it and lots of other both living and non-living reasons why it's much more stable than Cedar Island. Cedar Island is retreating rapidly before our eyes, and the people we visited some of the people that live here, and they said, yeah, I mean, I didn't used to be able to see the barrier island, now I can from the coastline. So Cedar Island is not being fed sediment the way that, you don't have to keep going if you don't want to. Cedar Island is not being fed sediment the way that Paramore Island is, and it's also not sitting on such a stable base. And the marshes behind it are also shrinking a little bit faster than Paramore Island. There's a lot of different things at play here. You can see two different sort of causes of marsh loss that occur when the systems are changing this way. One is just these back barrier lagoons widening almost directly due to sea level rise or to wave action that breaks up the edges of the marshes. And you can also see that when this was especially evident in Cedar Island when it's moving backward, that the sand line of the beach just rolls back over the top of the marsh, and we call that barrier rollover. And so it's difficult to say what happens to the marshes, the sediments of the marshes, when a barrier island rolls over a marsh versus when the marsh is drowned, and I'll get back to that later, but it's a big open question in this research. So I may have been interchangeably using the words stock and flow or sequestration and storage, but what I mean when I say stock is the actual carbon in the soil or the biomass that is not in the atmosphere doing any kind of additional climate-related damage. And when I say sequestration or flow, I'm talking about the additional carbon that's pulled out annually every year into the marsh system. So the marsh system, as all of you know, and I'm sure I'm preaching to the choir, is that marsh systems are highly undervalued as climate change mitigation tools in terms of the amount of carbon that they can pull out of the atmosphere and keep in their biomass and soils. The graph on the left deals with stock and shows you that salt marshes, which are our ecosystem of interest, store a lot of soil in their biomasses when you compare them to a typical tropical forest. And that's what puts them over the edge in terms of their capabilities of keeping carbon sort of inert and not in the atmosphere as a carbon well. And the right one shows tons of carbon equivalents per hectare per year that is taken up by the ecosystem per hectare. So you can also see that blue carbon systems are absolutely stellar at that compared to terrestrial forests. And a big reason for that is also because of the soils. Marshes are constantly vertically accreting, and you don't really see that so much with the tropical forest. Those are very nutrient poor systems that are really fairly stable in terms of the amount of biomass that's being built any given year. Unless it's a new forest. We're talking about old growth forest here. So I got my data to try to capture what's happening in these marshes over time from the CCAP program here at NOAA. So if any of you worked on that, thank you so much. It was very useful. So the CCAP program is Landsat imagery of the entire coastal area that classifies it into land cover types. And I have data points from 1992, 96, 01, 06, and 2010. That's because that's what's available right now. Hopefully sometime soon, 2014 will come out sometime before I publish, because then I could add it and we would have even more data. So this is a short-term, relatively high-resolution study. And these are my systems. And I broke them up by island because, as I've been saying, each island is going to be doing something different. So I don't want to look at the whole system holistically as all the way down from New Jersey to Fisherman's Island, because that wouldn't make sense geologically. So I split them up into different systems. I put Delaware together. I split up Assateague into Virginia and Maryland because the Virginia barrier part of Assateague has been nourished and is managed differently than the Maryland side. So again, we're thinking about capturing the geology, the differences in the geology between areas. And then we have all of these Virginia barrier islands that I mentioned earlier that are managed by the Nature Conservancy, or I should say not managed, they're just left as they are. And this, if you're familiar with the area, I combined Wreck, Myrtle, and Ship Shoal Islands into one system because the tidal channels that separate them are very ephemeral, and so it's sort of hard to say year to year which island is supposed to be which island. So I grouped them as one system because over time they have started to feed into each other so much that it's hard to separate them out. And finally, at the very bottom of Delmarva, we have Fisherman's Island, which is taking up a lot of sediment that is flowing downstream from here. And you'll see a little bit about what that means in a second. So this is the same part of Virginia with the marsh loss colored in red and the marsh gain colored in yellow. It doesn't really look like much from this far up, but it's a significant % change in some of the islands. In other islands, not so much. These islands have a lot of action, which is why I zoomed in on them. The Wreck Myrtle Shoal system is really, really dynamic, and you can see a lot of the marsh loss is occurring because of that phenomenon that I was showing you earlier, where the beaches are rolling over the marshes. So this area here was once classified as emergent wetland and is now classified as something else. In this case, it's probably beach or bare land or open water. In some cases, we had some pixels go from emergent wetland to developed land or emergent wetland to grassland in some areas, but the most dynamic ones were open water and beach, bare land. And you can see all that sediment is getting dumped in Fisherman's Island, which was the only island to have a significant, the only marsh system to have significant growth. So after looking at taking up the marsh area per year in my data points, I just made a simple linear regression over time for marsh area for each island. And I tried out different regressions because I was like, linear has to be too easy. There's no way it's just linear. Linear was the best fit. So the marsh area change over time gives us these coefficients of change. So you can see Fisherman's is the only one with a positive coefficient of change in marsh area. And I forgot to add the stars that show whether it's significant. That's my bad. That's a big scientist mistake. This one, these guys, the Cedar to Wreck Myrtle Shoal area was all significant in the loss of marsh area over time. 2 of these were significant. I think it was Assateague and Virginia. I have the coefficients in a table at the end that I can pull up later. And some of them were not significant changes. And that was more often observed in island systems that are managed by humans, which sort of makes sense because we're not allowing the barrier islands to roll back in those systems. And that prevents that type of marsh loss that I mentioned earlier, the rollover. So the rate of gross loss across the entire region was about 0.5 kilometers squared per year. The net loss, when you take into account marsh gain, was about 0.38 kilometers squared per year. So there is a little bit of marsh building going on, but it doesn't counteract the loss that's happening. So this bar graph shows you gross loss over time. The colors represent loss due to barrier rollover, which is those islands rolling back, and the black bars represent everything else. So originally we wanted to say that the loss that wasn't rollover was probably due to pure drowning of the marshes, but it's kind of hard for us to say that definitively without getting a better on-the-ground look of the geology of the islands. So we're just kind of saying other. And the way that we teased out what was lost due to rollover versus what was lost due to anything else is that we looked at the border of the island in one year, and if a marsh pixel was behind the island in the year before, and it was either on the island or in front of the island in subsequent years, that indicated that that marsh was rolled over by the island. And that marsh pixel was typically changed into either beach or bare land, or grassland, or open water. So that required a close look at each island to delineate what types of loss was happening. So then what we wanted to look at is, what is the marsh changing into? I've touched on that a little bit, but it's almost exclusively, all of the dynamism is reserved for these types of land cover. And you can see that the most exchange is happening between open water and the beach bare land category of the land cover classifications used in NOAA's CCAP. And a negative value means that marsh was lost and it was changed into that type of land cover. A positive value means that that marsh was built and it was taken from this other kind of land cover. So our most dynamic island is again Wreck Myrtle Shoal. Lots of transfer into beach, bare land, or open water, and a little bit that was built back. Interestingly, the only place where we see marsh being turned into developed land is up here where all of the humans are. That's actually not that interesting. So Fisherman's Island is the only one where you can see a net gain going on. All right, so after we had taken a good look at what was going on with the marshes, are they going away? If they're going away, what are they turning into? We moved on to try to place some kind of dollar value on that blue carbon. And I'm sure several of you, if not all of you, are familiar with the concept of the social cost of carbon, which is a term that tries to capture the economic cost of one additional carbon equivalent being added to the atmosphere. And they're usually estimated using these really big, complicated models that take biological parameters, socioeconomic parameters, and mash them together and try to place a value on 1 ton being added to the atmosphere. I'm using a value from a recent Nature climate change paper by Nordhaus in 2017. He places it at 33.1 per ton of carbon, or megagram, and that's in 2017 USD. But he also places an annual growth rate of 3% on that, which means that every year additional carbon being added to the atmosphere is going to cost us more because of the stacking effect of those damages. And there are a lot of pros and cons to using different models for this, and I'm sure some of you can tell me all about those pros and cons. So I would welcome that type of discussion later on. I should have put this slide earlier. I already told you that when I use these terms, I mean these things. It can be a little bit confusing in writing, so I try to make it abundantly clear. And we're going to start with storage, meaning I wanted to see how much carbon is already behind barrier islands in wetlands and their soils as of 2010, which is my most recent data point. So this is actually a really simple set of math that just takes the area of the wetland, 1 meter of soil depth, because that's the standard for how far down carbon-rich soil is usually found. Although it's actually rather conservative. In most marshes, if you go below 1 meter, it's still going to be carbon-rich soil. Plus the density, this is the average density, average soil carbon density across the region, which I took from literature measuring data points all around the different barrier islands. And this is actually pretty variable across islands, and it's part of another paper in this Sea Grant project to look at the variability in carbon storage in marsh soils in the region and add that to the final version of this model. Plus the social cost of carbon, plus a molar conversion to go from carbon to carbon dioxide equivalents. So as you can imagine, the number that you get for carbon storage is pretty much directly correlated to the area of wetland that exists, because everything else is held constant between the different islands. So that means that we're basically just looking at a graph of marsh area. I kind of tried to decide between showing you marsh area versus not, because this is the same thing. But it's transferred to show you the carbon storage that's behind those barrier islands. Wreck Myrtle Shoal is my largest system, which also helps explain why it is the place where the most action is going on. Although the Assateague system actually covers more raw square kilometer, but its back barrier lagoons are much larger. If you've been to Assateague, you know that you drive across water before you get to the barrier. And you can see that there's just not much storage going on in these much smaller barrier systems. So the idea behind placing a dollar value on this carbon stock is that if this carbon is disturbed and remineralized to the atmosphere, there's a big question mark about whether or not it becomes part of the atmospheric system and accelerates global warming in some way or contributes to it. We don't know how much of this carbon would be remineralized and contribute to the atmospheric carbon stock. It's just very hard to say. The literature kind of ranges between 25% and 100%, which is wonderful, just very specific. So it's very difficult to say whether or not when or if, let's say Wreck Myrtle Shoal, the barrier island crashes into the mainland and there's no more barrier system in that area, does that mean that $400 million worth of carbon will be released to the atmosphere? We don't know, but it would be pretty unfortunate if it did. Moving on to talking about sequestration. So we're sort of shifting gears to think about not what's already there, but what's being added each year, sort of like a stock portfolio situation. And the carbon sequestration rates have to be tailored to the land cover type, because I can't just say that if that marsh is lost, then no carbon sequestration is taking place, because that may not be true. If the marsh is being converted to open water, there actually is a small amount of carbon sequestration that's done by open water. So in my formula, I had to look at, that's another reason why we had to take the land cover dynamics, is so I could capture how much was being changed from wetland to these different types of land covers. So if it starts as wetland and a certain percentage of it becomes grassland, I can say that percentage dropped from 200 to 40. So the annual value of 1 square kilometer is represented by lowercase v prime, and that's V for value. I sort of wish I didn't pick V, because a lowercase v and an uppercase V looks the same. You'll see why that's a problem later. But the annual value of sequestration is going to be the wetland sequestration rate times the social cost of carbon times this molar equation, this molar conversion factor. So all that really tells us is that the wetland sequestration rate times the social cost of carbon is just how much is being added each year and what that's worth. And if we want to take it down to what's lost when it's converted, all you do is subtract the wetland rate from the new land cover rate and multiply that by the social cost of carbon to get the value of that change. It gets a little bit more complicated when you add in all the different percentages of what's changing to what, but this is the version that is much easier to talk about. So the uppercase V, which you wouldn't have known as an uppercase V if I didn't tell you, is the sequestration asset value as opposed to the annual value. So the asset value represents the value of that carbon, of that square kilometer being preserved in perpetuity. So we're saying it's going to be there forever. It's going to keep taking carbon out of the air for us, and that's what the value of that service is. So this leads me to talk about a concept in economics called the discount rate, which is a little bit hard to explain. The way that it was explained to me is that it's an economist's attempt to numerically capture the human tendency to value what is given to us now much more than what might be given to us tomorrow or the next day or in a year. We do the same thing with something bad that might happen to us. We are very much aware that if you tell someone climate change is going to cause you to lose your house tomorrow, that's going to freak them out a lot more than it's going to make you lose your house in 50 years. So a discount rate tries to put it's a very broad term, a broad definition of the term discount rate, but it tries to put a number on that. It also, in a lot of economic calculations, it's the same as the interest rate. And the reason for that is because you have to think about, let me see how I can explain this better. If you are going to use your money for something, you could always be using your money for something else. And you want to be able to capture what you're missing out on by not doing that other next best thing with your money. And the other next best thing in most scenarios is investing it. So a lot of the time, economists will use the discount rate as the interest rate to say, over time, if money is being used for this purpose, the next best use might have been investing it. So in this case, what we're using our valued service for, not literal money, is storing it and not having it be in the atmosphere. And so when we think about something that's going to happen in the future, meaning the carbon being taken out of the atmosphere that's happening years from now, we have to discount it because humans value that service less than they would if it was happening today. So that's the equation that captures discount rate once you simplify it out into perpetuity. And the asset value that's lost is the lost annual conversion, also taken out into perpetuity. So basically, it gives you the same annual value every year, decreasing just a little bit every year until it gets to 0, because it's so far out in the future that we don't care. And G represents the growth rate of social cost of carbon. So what is 1 square kilometer worth after all of that? The stored carbon in 1 square kilometer is worth 5.89 million carbon, US dollars. So that means that in 1 square kilometer, that square kilometer of wetland is holding back $5.89 million worth of carbon. And if that square kilometer is lost, maybe it will release all of that? Question mark. The value of sequestration, or additional carbon being taken out of the atmosphere, for 1 square kilometer is about $27,000, which is not as significant. And if we consider that it's going to keep adding that $27,000 worth of carbon every year into perpetuity, that eventually adds up to 5.36 million USD. And it's sort of a fun coincidence that these numbers are very similar. So the carbon stock of flow of 1 square kilometer left in perpetuity in this region adds up to 31.57 million. So after this, we had to consider what would happen to the wetland given different loss scenarios. So the truth is that these wetlands are not going to be there forever, and they're not going to be sequestering in perpetuity. So if they are changing at a given rate K, how can we capture the value of that square kilometer or that barrier system given the rate of change K? So you basically multiply the asset value by the rate of change, discount it again, because we're discounting the change itself instead of the service, which is a fishy concept to explain. And then you're basically capturing your lost value, and it goes out and it continues to decrease until there is no more wetland left. So you have to take K times the total area of wetland to see how far out it goes, and that's when the simulation stops. Because we're not going to keep losing money if there's nothing to lose. So we have 4 loss scenarios. One that is the net change in Marsh that's happening right now, according to the data I got from CCAP, that continues happening at a constant rate. Likely not very realistic. It may accelerate, it may decelerate. Loss scenario number 2 looks at local sea level rise taken from NOAA gauges in Virginia, Maryland, and Delaware, and looks at the relationship between sea level rise and marsh change and uses that value to estimate how much marsh will be lost given that the sea level rise continues at its current rate. Again, we don't think it's going to continue at its current rate. It's probably going to accelerate. That's why I wanted to use the IPCC scenarios for sea level rise for this region, because that captures a little bit more of the potential acceleration that may occur. And loss scenario 3 uses RCP 2.6, and loss scenario 4 uses RCP 8.5. So I wanted to use the ones that would be the most conservative climate change mitigation policies are enacted. Sea level rise happens very slowly and eventually slows down. And I wanted to use a version where very little action is done and sea level rise happens very quickly to show us the change in value that occurs if this happens very quickly versus if we can make it happen very slowly and we have time to adapt, or the marshes have time to grow. So this is the results of those 4 loss scenarios. Loss scenario 4 stands out because that's the one, the IPCC scenario, where sea level rise accelerates and happens very quickly. And that tells us, because it's so much higher, that the rate of sea level rise really matters. If this happens very quickly, it's going to be a lot more damaging for us than if it happens very slowly. That's partially because what we've been talking about, humans just value changes that happen tomorrow more than they do other things. but it's also because it gives us less time to adapt. So this only numerically captures that discount rate, which is supposed to be humans valuing changes that happen sooner rather than later. Loss scenarios 1 and 2 are very similar to one another because the relationship between sea level rise and marsh change in this region is very, very tight. So using sea level rise to model change versus using marsh area to model change ends up not being very different because those two things have a very close relationship. And the scenario with very conservative mitigation policies looks a lot nicer. There's a lot less loss. The upper bound of these bars represents a situation where not only is the annual asset value lost, but the carbon stock that's already there gets released into the atmosphere, and those damages that are being prevented by storage do occur because the carbon is out. The bottom one represents that none of that stock is released. It gets buried under the ocean or the beach sediments, and it's, hey, at least we didn't lose that kind of thing. So it could range from just about 50 million for this wreck Myrtle Shoal, which I keep using as an example, to 150 million, depending on how much of that carbon stock is mobilized. So if nothing else, this study tells us that it's really important for us to know what's going to happen to this stored carbon in marsh soils. These are the actual values that were in that bar graph from beforehand, just in case it was difficult to read, but it's summed up for all of the region. So for the whole region, and let's say we're looking at loss scenario 1, which is marsh area change continues at the same rate it's been happening. The sequestration value, or the asset value, the annual additions that's lost, is about 63.36 million. So that's our lost opportunity to take carbon out of the atmosphere in the future because that marsh won't be there anymore. Then the upper bound of carbon stock loss represents the value of if all of the carbon in the region is released by the marshes being destroyed, 66.3 million, and then the upper bound is if you add those 2 points together, very simply. So the key points to take out of this is that there is a significant net loss happening region-wide. It's not even across islands. Some islands are much more dynamic than others. The average net loss is 0.38 kilometers squared per year. The 3 states have significantly different rates of loss, Virginia being the one where most of the loss is happening. Virginia and Delaware's wetlands are smaller than, Maryland and Delaware's wetlands are smaller in the first place, but they're also experiencing less percent change. Maryland has spent millions of dollars on barrier island nourishment since 1992. Delaware has spent even more. And when you compare these values to what I showed you on the last slide, it actually turns out that management is really expensive anyway. So we actually have to realistically say, this alone may not be enough to justify all that money. But that's not what those managers are making their decision based off of. They're not thinking about blue carbon like I am. They're thinking about rich guys' second home. So they might place, that dollar value might look really tiny compared to all those guys' second homes on barrier islands. But the question is it going to be worth it to them to save the blue carbon in the islands that are not inhabited? And the answer may be no. But this still represents a large amount of additional damage from released carbon, depending on what happens. The annual value of 1 square kilometer is 27,000. At the current rate of loss, the lost asset value for the whole region is 60. We just saw this. If preserved in perpetuity, just 1 square kilometer is worth over 5 million, which is useful to know, at least according to these numbers. If all the Delmarva wetlands remain, the asset value is very large. We should want to keep them. Marshes in the Mid-Atlantic barrier systems currently store 16.8 gigagrams of carbon, which is quite a lot of grams. And if they are released, they could cause $2.11 billion in damage. So I think that number is old. So adding information from the 1800s is our next step. This is a short-term, high-resolution study, which has some disadvantages. It doesn't capture the long-term change that's occurring in this region. However, if you deal with this type of thing, you know that it's much harder to get geological data from 100 years ago. So we're working on digitizing maps from the 1800s and experiencing a lot of difficulties. But ideally, when we do publish this, it will include a long and short-term view. And we want to elaborate the model. This paper will probably get published as a blue carbon paper, cross fingers. But in the future, we want to create a more holistic model that also includes values of things such as biodiversity and the homes that are on some of these islands. These are some key references. And these are my acknowledgements. I have to thank Sea Grant and all of the wonderful people that supported me. This was my master's thesis research that has been only just a bit modified since I put it in the world. And that's it. Questions? Thank you.
Sarah? Great job, Meredith. That was really, really informative. Beautiful. I might have missed this, but when you were talking about the numbers specifically of carbon, did you also look at the numbers if the islands were to go away, what the effect would be on like storm surges or effect to like not the islands, like the mainland?
Right. So the question was whether or not we've looked at values for losing barrier islands that are not related to blue carbon, such as potential additional damages from storm surges and other impacts to the mainland. That's part of the larger Sea Grant project that this sub-project is under. I personally cannot tell you anything about that, regretfully, but some of my colleagues are including that in their model because it's very likely that that type of thing is a much more valuable ecosystem service, which is not to say that this is not important, but yeah.
Could you say a little bit more about what you mean by nourishment and how that preserves or increases the amount of wetland as opposed to just an island?
That's a good question. Oh, I didn't realize. Okay, sorry. So he asked if I could speak a little bit more about nourishment and what that means for the whole system, including the marsh, besides just adding sand to the barrier island. Because that's what nourishment is adding sand to usually the forefront of the barrier island, typically because beachgoers want more beautiful sand to lay on, but also because it actually does have a significant effect on the movement of the barrier island. So if you dump a bunch of sand on the front of Assateague Island, that is going to slow that island's inward transgression, just because much of the inland transgression is wave action against the barrier island. And if you keep moving that point further out to sea, that's going to increase the amount of time it takes for the island to move forward. It's not a perfect relationship at all. For example, if sea level rise is occurring in the back of the island, that's still going to cause breakup and drowning of wetlands. So it's not saving the wetlands or anything like that. But it does slow the transgression part of marsh loss. So it is only one piece of the puzzle. Does that answer your question?
So is it worth it to do that?
She asked if it's worth it to do that. If you just look at my numbers, if you only compare blue carbon versus nourishment, the answer is no, if what you're thinking about is just money. If you add the damages from storm surge, the loss of nursery, the value of a nursery ecosystem, that number may look different, that balance may look different, but I can't speak to that yet.
So when they look at the amount of carbon that's stored or sequestered in the system, they're assuming that all of that carbon is derived from the atmosphere, or are they considering that in some cases carbon is being pulled from the aqueous phase? And if you're pulling it from the aqueous phase, the reaction is such that oftentimes you actually generate CO2, actually partition carbon out of the water phase. This is what happens on a coral reef. Coral reefs are in fact net sources of carbon in the short term to very long term. Mm-hmm. The carbon is being pulled from the aqueous phase, which results in a partitioning such that you actually want that carbon being liberated from the water into the atmosphere. So do they examine the differences? So I don't know enough about wetlands to know where the carbon is being derived from. All those organisms are in fact pulling the carbon from the atmosphere.
Okay, so this question, so he asked whether you're looking at carbon being pulled just from the atmosphere or if you're looking at carbon being pulled from the aqueous phase, and basically how do they determine how carbon is being added to the system. So my understanding is that this number, that 0.047 that I had up earlier, is measured by looking at how much carbon is added to the soil year to year, regardless of where it comes from. So that means that we're excluding any carbon that's being added to the above ground biomass, which is another potential issue. But it does mean that we're just looking at the raw change in the amount of carbon in the soil. I hope that answers your question.
It sort of doesn't matter.
Well, it does matter.
It doesn't tease it out.
Yeah,
That's storing it.
not quite. So, no, I mean, one of the ways the planet compensates for long, for periods of very high atmospheric carbon is it shuts off gasification. Reefs, when reefs are shut off, they actually serve as that actually stops carbon from being emitted from the ocean. So, I think it's a nuanced question that we might want to look at. There is a considerable difference in terms of the amount of carbon fluxed into the system or out of the system, depending on whether the carbon is going to be directly from the atmosphere or if it's being pulled from the aqueous phase. So I think it's an important question. Because we were talking about this years ago when people kept wanting to put coral reefs and saying they were sinks of carbon. And we kept saying, no, they're not. In fact, they're a net source of carbon. And if you go into these wetland areas and measure the partial pressure of CO2 in the water, I don't know, but frequently they're very high CO2 systems because of the amount of respiration that's actually being generated.
Right.
So they are putting biomass carbon into the ground, but you need to, but that's not, you have to look at the total exchange of carbon and where it's all coming from.
That has been a point of contention in several of our meetings. Not that specifically, but sort of the question of whether or not, mainly the question of whether or not wetlands reach a point where they become a sink or a source, whether they just always are a little bit of both, because they do seem to be a source of methane. It's an important and mostly unanswered question as far as I know. But thank you for bringing it up.
We have a question online and they would like to speak because the question is rather long. So Kenneth, if you can go ahead and ask your question.
Yes, thank you. I enjoyed your talk, and I was a student at VIMS through about '87, and I completed my dissertation in exactly the location you're working on now, on the geologic history of the Holocene and Quaternary geology of the area. And my debate on this with you, and also was with Chris Hine from VIMS, is that what I had found, especially towards the south, around behind Smith Island, was that as the islands move back, you wind up having more salt marsh growth due to the constriction of the back barrier area, lessening the tidal prison, lessening the fetch of possible waves that are back there. And I can show you from both maps from the cores I took, and from an area where I photographed over 5 years, which showed the tidal flat turning into alterniflora and the alterniflora turning into patents, that I was getting marsh growth there, and considerable marsh growth. And again, the studies ended around 1990 because I graduated and moved on to NOAA. But my premise is that you're actually, as the islands move back, due to this constriction, you'll be actually getting more salt marsh than less.
Okay, I have heard of this from Chris Hine. And I think that it's a question that he is a lot more equipped to talk about than I am.
I've argued with him a bunch of times about this.
So. I'm sure, yeah. And that's what I would say. He and I have talked about this concern too. And for the time, we're continuing to use the recent marsh loss as a way to model future change, rather than in this particular study that I'm working on, rather than looking at the dynamics of the tidal prism. And so that's why I think it's probably better for you to keep talking about it with him than with me.
Well, what I'm just trying to get at, and I think you did just address this, is that depending on which island you're talking about, you're going to get varying amounts of growth and loss. And I think when you just throw a number out and use the Myrtle Island behind Myrtle Island and use behind Smith Island are very, very different, or behind Cobb Island, especially different, where it's very, very open water. In fact, it makes it just more complex, more variable, and allows us to be more like geologists and not have an answer for you.
Yeah, and I agree that it's not a good move to try to generalize across these islands, and we're trying to drill down to that. So thank you for the reminder.
Okay, thank you.
Is there any more questions in the room?
Do you have any plans to look at the biomass, the carbon stored in the biomass? Because I noticed you didn't include that.
Yeah, that's another one of the people who's a partner in this Sea Grant, Karen Giddin. She's actually at the University of Maryland, I think. And she's looking at more fine scale, what's the biomass being added year to year and how is that variable across both between the front of the Barrier Island to the mainland, like across that transect, as well as between islands. She is an excellent person to talk to about that. Yeah.
Did we have one more question?
Good.
Okay. Thank you all for coming. Thank you, Meredith. And come back for the next Knauss Brown Bag next month.
Thank you. Thanks online.